Hello and welcome. In this video, we're going to talk about the volume of a revolution of a curve around both the x and the y axis. So in the next video, we'll build on this and talk about what happens if we have two curves that are being rotated. And then in the video after that, we'll talk about what happens if we're rotating around a line that is not the x or the y axis. So let's go ahead and start thinking about what it looks like to rotate a curve around an axis. Okay, so the first thing that I want you to think about is what happens if you have a line or a piece of a line segment, and you actually spin it around. What happens when you spin a line around? And I'm hoping that you can see that if we spin a line around, we're going to get a circle. So if we spin a line around and get a circle, and I'm going to try and show you, if I spun this around in a circle, if I spin anything around in a circle, right, I'm going to have a circle. But what we've talked about is that integration is the area under the curve. So what if I created this area and I spun this area around the curve? What would that look like? Well, my three-dimensional drawing skills are lacking, so I'm going to try and pull in a visual for you. If I spun, so this is that same curve, f of x equals 3, and if I spun it around, I'm going to get a bunch of circles. And if I filled in that volume that I'm creating, if I filled in all of those circles, I would get sort of what looks like a cylinder or what looks like a disc. So if we take area and we rotate area around an axis or around a line, we're going to get volume. So let's focus specifically on this cylinder for right now that we're creating if we rotate this around. And I want you to be aware the scale factor here looks off. This is going to be 3, even though it looks like it should be at 2. That's my bad. If we took this and rotated it around, if we took this area under the curve, this square rectangle, and rotated it around, we could find volume. So let's think about that volume just in a geometric way first. How we would have done it in geometry. To find the volume of a cylinder, we take pi r squared and we multiply it by the height. So we take the area of the circle and we multiply it by the height. In this case, the radius would be the function, the distance from our function to the x-axis, which is 3. So volume equals pi times 3 squared, and the height would be what's happening with our x-axis. So the height would be the change in our x, which is 2, because it's going over to the right 2. So our height would be 2. So we could find the volume. Using basic geometry, we would get 18 pi units cubed as our volume. So just like we talked about in the previous video, if we then took, instead of this perfect little rectangle area that we rotated to get a perfect little cylinder, what happens if we take an actual curve and we rotate it? It's not going to create a volume that we have this beautiful formula to evaluate. So before we move on to something more complicated, I want us to think about, can we look at this same problem that we just figured out how to solve, and can we find the volume using calculus? So if we know that the area under the curve is just the integral of the function, right, or the integral of two functions potentially being subtracted, if we know that that's how we find the area under the curve, the volume under the curve should be the integration of that area. And if you think about that, it's like I'm taking an infinite number of little discs or little mini cylinders, and I'm adding together the volume of each individual little cylinder. So if volume is going to be the integral or the sum of all of the areas of these little teeny tiny cylinders, we're going to be looking at volume being pi times the integral from wherever we start to end the area that we're talking about of our radius squared with respect to x or y, depending on what our function looks like. So if you look at this formula, I want you to notice we still have pi and we still have r squared, just like we have pi and we have r squared. The other thing that I want you to notice is that h is coming from our integral and its bounds, and this dx is saying as we change the height, as we change our x's. So each part of this basic formula, pi r squared h, is still playing a role in our integral version. So let's see if this works on the problem that we already found the volume to be 18 pi. So we would be integrating pi times the integral from 0 to 2 of our radius, which we said is 3, which is just our function, squared, with respect to x. And if I do this, 3 squared is 9. So if I integrate 9, I get 9x, and I'm evaluating that from 0 to 2, and that is also going to be 18 pi units cubed. So let's look at number 2. Let's try and extend this a little bit and see if we can find the volume of this not so simple solid that's being created by taking the area under the curve, negative x squared plus 4, and rotating it around to create sort of like a bowl shape here. So we're looking at this, and I'm turning it upright so you can see it a little better, but we're trying to find the volume that's created when we rotate our solid here. So first things first, we know that we're going to have pi times whatever our radius is squared, and our function is in terms of x, and we're rotating around the x-axis right now. So what is our function? Our function is our radius. Our radius is negative x squared plus 4, because every single cylinder that's forming goes up to this curve. That's how we're figuring out what the radius is. So I'm going to put negative x squared plus 4. And how do I deal with my height? Well, I think about where does this volume start and where, or area start, depending on before or after the rotation. And where does it end? Well, it starts at 0 and it ends at 2. Now, everything after this is really just a review on integration strategies. So what I'm going to do is I'm going to expand this polynomial. This is going to give me x to the 4th minus 8x squared plus 16. And then if I integrate this, I'm going to get pi times x to the 5th over 5 minus 8x to the 3rd over 3 plus 16x, evaluated from 0 to 2. And we're going to plug in those values. So 32 over 5 minus 64 over 3 plus 32. And if I plug in 0, I get 0. And to save us time, I'm going to just tell you that if you find a common denominator, which would be 15, and you get that common denominator and combine your fractions, you're going to end up with 256 pi over 15 units cubed. So really all we're doing is saying pi r squared times h. R is your function, and we're going to talk about in different circumstances where we might have to look at what our function is, what volume our function is creating. But for right now, r is our function. We're going to square that and integrate over the x values at which we're creating this volume. So let's look at 2 more examples where we're rotating around the x-axis. All right, here we go. So the idea here, determine the integral that would be used to find this should say, volume, not area, of the solid resulting from a revolution around the x-axis. So that's telling us we're going to integrate with respect to x, and then find the volume. So volume equals pi times r squared times height, or in this case, pi times the integral of r squared. Looking at the graph, we can find the bounds. This is going from 0 to 2. And looking at our function here, we can find our radius. Now, we're just going to expand. So this is x to the 4th plus 8x squared plus 16 dx. And then we're going to integrate. This is going to become x to the 5th over 5 plus 8x to the 3rd over 3 plus 16x. This is really similar from 0 to 2 to what we just did. So I actually encourage you to pause the video and to do the common denominator work to make sure you can get through this. But after you do that, you're going to get 896 pi over 15 units cubed. All right, let's see if you can set this last one up on your own. Volume is pi r squared h, or pi times the integral of r squared with respect to x. So go ahead and pause the video and see if you can work through it on your own. So hopefully you had time to pause the video. This is going to be pi times the integral from 1 to 3 of r squared, which is 5 minus x quantity squared dx. Now I'm going to have you pause the video and actually evaluate that integral and just do a little practice with integration, and then unpause the video and see how you did. So hopefully you had enough time to work through that and you can check over your work here, but you're going to expand, then you're going to integrate using the power rule, and then you're going to plug in your bounds, find a common denominator, and simplify. Make sure you have unit squared at the end. So we're going to take this just one step further in this video, and we're going to ask ourselves, how would this be different if instead of rotating around the x-axis, we rotate around the y-axis? So the short answer to how is it different when we integrate around the y-axis, or if we rotate around the y-axis, is that we're going to integrate with respect to y. So that means we need dy, we need bounds that are in terms of y, and we need a function that is x equals stuff in terms of y, or f of y equals stuff. Other than that, it's really the same process. We're still identifying our bounds, our function is still our radius, and we're integrating pi r squared to come up with that volume. So let's look at this problem here. Again, we're looking at the volume is the integral of pi r squared, but now the big difference here is that we're going to be looking with respect to y. So all things with respect to y. Well, our function here is already with respect to y. So 4 minus y squared is our radius, because now we're forming our radii this way because we're rotating this way. So this volume would extend this way. It would be more like this kind of bowl. Okay, so our bounds also need to be in terms of y. So we're going to look from here to here. And again, this graph is not great. I apologize. The bounds there are going to be from 0 to 2, because if y is 2, this is going to be 0. Actually, our bounds are okay there. So go ahead and pause the video and work through this integration on your own, and then unpause the video and see how you did. So I'm going to come over here to give myself some space. We're going to expand first. So the integral from 0 to 2 of y to the 4th minus 8y squared plus 4 dy. Man, I really liked to pick this function that has basically the same antiderivative each time, but oh well. Plus 4y. 4y? No, not 4. This should be 16. This should be 16 from 0 to 2. And if we plug in the bounds, 32 over 5 minus 64 over 3 plus 32 minus 0. And then again, I'm going to jump to the common denominator and combining like terms, 256 pi over 15 units cubed. So we're going to work through just 2 more examples where we're rotating around y, and then that really is our intro, our first lesson on volume created by rotating a function around the x or y axis. Okay, for number 1 now, we're determining the integral that would find the area resulting from rotating this half circle or semicircle around the y-axis. So if we rotated that, it would look like a sphere. So if we're finding the volume here, we're saying pi times some radius squared with respect to y, because we're rotating around the y-axis. So let's go ahead and plop our function in there. Our function is our r, which is the square root of y, and we're integrating from one y value to the next, so from 0 to pi. If we simplify this, we get sine of y dy from 0 to pi. What do we integrate to get sine? We integrate negative cosine, and then we're going to evaluate that from 0 to pi. So I'm actually going to take this negative out, negative pi times cosine of pi minus cosine of 0, which is negative pi times negative 1 minus 1, which is 2 pi units cubed. All right, I'm going to encourage you to pause the video and work through number 2 on your own, and then unpause the video and see how you did. All right, hopefully you have had time to work through this. The volume is going to be pi times the integral of some r squared dy. Now, our r value is the square root of y, and if we're looking at the y's here, we're going from 0 to 2. So this is pi times the integral from 0 to 2 of y dy, which is pi times y squared over 2 from 0 to 2, which is going to be pi times 4 over 2 minus 0, or 2 pi units cubed. One thing I do want to point out is if you have an equation that is written like y equals x squared, and you're being asked to rotate around the y-axis, you need to solve this for x. So you would square root both sides to get x equals the square root of y. So you could do a problem like we have here where we're rotating around the y-axis. So anytime you're integrating with respect to x, your function should be with x's, your bounds should be with x's. Anytime you're integrating with respect to y, your function should be in terms of y. Your bounds should be in terms of y so that you can integrate with respect to y. So, big idea in this section, we are taking the area bounded by an axis and rotating it around in order to get a bunch of little cylinders to add up together using integration to find the volume. So we're really just integrating pi r squared, and the integration becomes our height. So we can be finding the volume of these solids. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.